Hi folks, we're going to take a look at question 21 from page 160. So we've got the equations of two planes, and they want us to figure out whether these planes are parallel and distinct, coincident, or neither. Now, if they were in Cartesian form, that would be much easier to do, and that's probably where we're going to end up going with this question. I think the easiest way to attack the problem. So in order to show that two vectors are parallel, easiest way is to show that their normal vectors are parallel. So I can take the direction vector and use the cross product to get a vector normal to the plane, and then repeat with the second one. Then from there we can tell whether they're parallel or not. Okay, and if they're not, we know for sure that we've got the answer. We can just say they're neither. However, if they are parallel, we'll have to determine whether they're coincident or distinct. So let's start with the normal vectors. So we'll start with -8, 1, -9. Okay, and the other one is -1, 5, 7. Okay, and let's find our first normal vector. So we have 7 minus -45, so 7 plus 45 is 52. Okay, then we've got 9 minus -56, so 9 plus 56 is 65, and then here we've got -40 plus 1 is -39. Okay, now I notice here that 52, 65, and -39, I believe, have a common factor, so let's simplify this normal vector. Okay, so here they're all divisible by 13, so 52 divided by 13 is 4, 65 divided by 13 is 5, and -39 divided by 13 is -3. Okay, so there's our first normal vector. Now let's find normal vector for the second plane. So we've got 1, 1, 3, and -2, 1, -1. And so here we've got -1 minus 3 is -4. Okay, so that's promising so far. So we have -6 plus 1 is -5. And then here we've got 1 plus 2 is equal to 3. Okay, and we see that these two vectors are indeed parallel. Hence we know the planes are parallel. So here I'll change this one here to divide everything by -1. So we've got 4, 5, and -3. Okay. Now that we know that they're parallel, we know that there might be coincident or they might be distinct. So this is where the easiest thing to do, I would say, is to write each of these in Cartesian form and see if the equations are scalar multiples of each other. In other words, if the d values will be in fact in this case here, will be equal, because I'm going to be using the exact same normal vector for each plane. Okay, so let's start with plane 1. And let's calculate the d values. So we've got 4 times, and 403 is on the plane, so I'll use that point. So 4 times 4 plus 5 times 0 minus 3 times 3. Okay, and so here we have 16 minus 9 is equal to 7, so d is equal to -7. And now we'll find the d value for the second plane, and since we use the same normal vector, the d value, if it's the same, we know they'll be coincident, and if the d value is different from -7, they'll be distinct. Okay, so here we'll take 4 times -14 plus 5 times 12, and then minus 3 times -1. Okay, and let's see what we have here. We have 4 times -14, so that is -56. 5 times 12, 60, plus 3. And so d is going to be equal to, well, -56 plus 60 is 4, plus 3 is 7. Bring that to the other side, -7. Okay, so the equation for both of these planes is just 4x plus 5y minus 3z minus 7 equals 0 for both. That means the planes are coincident. Okay, so just recap of what we did is we know to show that two planes are parallel, we have to show that their normal vectors are parallel. So we use the cross product of the direction vectors to get our normal vectors. We showed that they were parallel, and then we wrote the equations of the plane in both in Cartesian form and showed that they represented the same plane, hence coincidence. Okay, that's it for this question.